Good evening. Welcome back, or if this is your first time here, welcome. Tonight we're going to explore something that surrounds us now, but started as a simple question asked nearly a century ago. We'll discover artificial intelligence slowly and patiently, moving through decades of patient research from philosophers wondering whether machines could think, through early computers the size of rooms, to systems that learn from experience, algorithms adjusting parameters in data centers while the world sleeps. We'll begin with people doing mental arithmetic by hand, questioning whether machines might someday calculate, stand beside Alan Turing as he formulates the foundations of computation, watch the first neural network learn to recognize patterns, and observe the long, patient decades of research that brought us to the present moment. This will take time, unfolding at the pace of research itself, one experiment at a time, one breakthrough followed by years of refinement. If this story helps you rest tonight, feel free to like or subscribe, though there's no pressure. I'm always curious where you're listening from, so if you feel like it, comment your city and what time it is there. Perhaps you're listening on a device whose operation depends on AI systems, pattern recognition in the speech-to-text that might have transcribed your search query, though you probably didn't think about the neural networks involved. Dim the lights now if you haven't already. Adjust your pillow. Maybe turn on a fan for some gentle background noise, or let the silence settle around you like the quiet of a research lab after midnight, computers humming, models training, parameters adjusting while researchers sleep. We have nearly a century of AI history ahead of us, but we'll take it slowly, one insight at a time, 1 year after another. Let's begin. Imagine you were sitting in a counting house in London, perhaps the 1850s or 1880s. The specific date matters less than the nature of the work you're doing. You're a clerk, though not the modern office worker that term suggests. Your job is calculation. You are quite literally a computer, though that word means something different in this era than it will come to mean a century later. It means a person who computes, who performs arithmetic, who transforms numbers according to rules. The room around you is filled with similar workers, dozens of desks arranged in rows, each clerk bent over ledgers, adding columns of figures, calculating interest, computing insurance premiums, checking others' work. The sounds are the scratch of pen on paper, occasional murmurs as someone double-checks a difficult calculation, the rustle of pages turning, footsteps of supervisors walking between desks monitoring the work. The smell is of ink and paper, lamp oil if it's evening, coal smoke from heating fires, the mustiness of old ledger books stacked on shelves lining the walls. The windows, tall, and providing the main source of light during daytime, show weather passing outside, rain streaking glass on wet days, frost patterns forming in winter, the sun's angle changing through seasons. The room's temperature varies with the weather, cold enough in winter that ink sometimes thickens, warm enough in summer that windows open and street sounds drift in. The clatter of horses, vendors calling, the urban symphony of the Industrial Revolution. Your desk is worn smooth by years of use, wood darkened by hand oils and ink stains that resist cleaning. The chair is hard, designed for posture, not comfort, encouraging the upright bearing considered proper. Your inkwell sits in its holder, occasionally requiring refilling from the large bottle kept by the supervisor, black ink that smells of iron gall and acidity, staining fingers despite careful use. The pen you use is a steel nib, requiring occasional wiping, scratching slightly as it moves across paper. Earlier in your career, you learned the proper angle to hold it, the right pressure to apply, the rhythm of dipping and writing that maximizes efficiency. These small mechanical skills, acquired through practice, become automatic, your hand moving through motions, while your mind focuses on the arithmetic itself. Your hand cramps from writing. You've been adding the same type of figures for hours, dozens of computations that follow identical procedures, column after column of numbers, carrying the ones, writing totals, checking your work by adding again in reverse order. The mental effort is real but mechanical, following rules learned through training, no creativity required, just careful attention to avoid errors that would propagate through subsequent calculations. The tedium creates a question in your mind, not necessarily articulated clearly, but present as a feeling. This work is mechanical. Each step follows precise rules. If machines can weave cloth following patterns on punch cards, if machines can print newspapers and manufacture goods, could a machine someday do this arithmetic? Would that constitute thinking? Or is thought something more than following rules? You don't know that similar questions are occurring to others in this era. Mathematicians performing calculations for astronomy tables, navigation charts, engineering projects, philosophers debating the nature of mind and consciousness, inventors sketching mechanical calculators that might ease the burden of computation. The question is forming across multiple minds independently. What is thinking, and is it something only humans can do? The work continues day after day, morning arrival at the counting house, hanging coat, sitting at desk, opening ledger, beginning calculations. Hours pass in the rhythm of arithmetic. Lunch break, afternoon calculations. Evening departure, eyes tired, hand cramped, mind numb from repetition. The pattern repeats weekly, monthly, yearly. Some clerks spend entire careers doing such work, becoming incredibly fast and accurate, human calculators whose brains execute algorithms as reliably as any machine might. But errors occur. A clerk misreads a figure, makes an addition mistake, transcribes a number incorrectly. These errors must be caught through checking procedures, multiple clerks verifying important calculations, cross-referencing totals. The human element introduces both flexibility and fallibility. A machine, if it could compute, would make different types of errors, mechanical failures rather than mental lapses, but would it be more reliable? The question lingers unanswered. Time passes. You find yourself now in a different setting. A university mathematics department perhaps, early 1900s. You're a mathematician, or maybe a mathematician's assistant, performing calculations for research. The work is more sophisticated than commercial accounting, but similarly mechanical in execution. Numerical solutions to differential equations computed point by point, following algorithms that are precisely specified but tediously long. Each calculation requires hours of work, and you perform dozens or hundreds to map out a function's behaviour. The question becomes more urgent in your mind. Surely this could be automated. The procedure is entirely algorithmic, no judgment required, just patient execution of defined steps. You've heard of calculating machines, mechanical devices, with gears and wheels that can add and subtract, some that can multiply through repeated addition. These help, but are limited, handle only simple operations, require manual operation, prone to mechanical failures. You imagine a more sophisticated machine, one that could follow complex procedures automatically, that could perform not just arithmetic, but the sequences of operations that constitute algorithms. This imagining is not quite concrete enough to be an invention, more a wish, a sense that such automation should be possible even if the implementation remains unclear. Others are having similar thoughts, tinkering with mechanical computation, but the technology of the era limits what's achievable. The philosophical question deepens. If a machine could execute algorithms, would it be thinking? You're following algorithms yourself when you compute, applying learned procedures mechanically. The thought is uncomfortable, suggesting human mental work might be less special than assumed, reducible to rule following that machines might replicate. But perhaps thinking involves something more, insight or understanding or consciousness that transcends mere calculation. Decades pass. Now imagine you stand beside Charles Babbage in his workshop, London, the 1830s and 1840s, though you're observing as a ghost might, present but not participating, watching as he designs his analytical engine. The workshop smells of metal and machine oil, the sounds are of metal filing and gear cutting, assistants assembling prototypes that demonstrate principles without achieving the full vision. The workshop is cluttered with mechanisms in various states of completion, partial assemblies demonstrating specific functions, gears and wheels laid out on benches, technical drawings pinned to walls or spread on drafting tables. Sunlight streams through tall windows during the day, illuminating metal parts that gleam when freshly machined, dust motes floating in the beams. The floor is wood, stained with oil, scattered with metal filings and wood shavings from patterns carved for casting. Babbage himself is intense, focused, explaining the engine's design to anyone who will listen, demonstrating prototype mechanisms, showing how carries propagate through number wheels, how the mill would perform arithmetic operations, how conditional branching could be implemented mechanically. His enthusiasm is infectious, but his perfectionism is exhausting, redesigning mechanisms, repeatedly seeking theoretical optimality, even when practical implementation becomes more difficult. The craftsmen working with him are skilled, capable of precision machining to tolerances measured in thousandths of an inch, creating gears that mesh smoothly, wheels that turn freely, mechanisms that work as designed when built in isolation. But the complete engine would require thousands of such parts working together, each dependent on others, tolerances accumulating across assemblies until the whole system might bind or misalign. The engineering challenge is formidable, even discounting the cost and time required. Visitors tour the workshop periodically, gentlemen of science and wealthy patrons, examining the prototype portions, watching demonstrations of the difference engine, Babbage's earlier, simpler design, performing calculations, trying to understand the revolutionary concept of programmable computation. Most leave impressed but uncertain, the vision grand, but the realization distant, the promised utility unclear compared to the enormous cost. Babbage has imagined something remarkable, a mechanical computer that could execute any algorithm expressible in its programming language. Not just a calculator for specific operations, but a general-purpose machine following instructions encoded on punch cards, the same technology Joseph Jacquard used for weaving looms. The engine would have a mill for performing arithmetic operations, a store for holding numbers, mechanisms for conditional operations and loops, everything needed for algorithmic computation. The design exists on paper in detailed mechanical drawings showing thousands of parts, gears and wheels and cams, assembled into mechanisms of staggering complexity. Babbage works on it for decades, designing and redesigning, building small portions to prove principles, seeking funding to build the full machine. The vision is correct, the understanding of computation profound, but the mechanical engineering required exceeds what the era can accomplish. The engine is never completed, remains a brilliant design unrealized. Ada Lovelace studies Babbage's design and sees something Babbage himself barely glimpsed. Writing notes on the analytical engine, she describes not just calculation, but the possibility of machines manipulating symbols according to rules, potentially processing not just numbers, but any information that can be encoded symbolically. She imagines the engine composing music, creating art, though always following programmed rules, never originating anything itself. Her notes constitute the first algorithm intended for machine execution, a program to compute Bernoulli numbers written decades before programmable computers exist. The question sharpens in her writing. Machines can manipulate symbols, but can they think? She argues no. Machines cannot originate anything, cannot have intentions or understanding, merely execute operations defined by humans. But the boundary seems fuzzy. If following rules produces intelligent-seeming results, does the lack of consciousness matter? The question will echo through the next century, never fully resolved. Years accumulate. The analytical engine remains unbuilt. Babbage dies, his workshop dismantled, the gears stored away. But the ideas persist, documented in papers and notes, waiting for technology to catch up to vision. Mechanical computation proves too complex, requires too many parts, too much precision. The industrial capacity exists to build machines, but not machines of this intricate interdependence. The dream waits for electricity, for electronic components that can switch states faster than gears can turn. Generations pass. You now find yourself in England again, 1936, though the scene is quieter, a young mathematician named Alan Turing sitting in a room thinking about computation in abstract terms. No gears and wheels now, just mathematical logic, symbols on paper, the pure essence of computing divorced from physical implementation. Turing is pondering a question posed by Hilbert. Can there be a mechanical procedure to determine the truth of any mathematical statement? To answer this, Turing invents an abstract machine, now called a Turing machine, a conceptual device that reads and writes symbols on an infinite tape according to rules specified by its state. The machine is purely theoretical, thought experiment rather than blueprint, but it captures something fundamental about computation. The room where Turing works is quiet, perhaps his rooms at King's College, Cambridge, the smell of old books and coal heating, the sound of pen scratching paper as he writes out his proof. The mathematics is dense, formal, using logic to analyze the limits of logic itself. But the conclusion is profound. There exist mathematical problems that no mechanical procedure can solve, questions that are fundamentally undecidable. Computation has limits, and Turing has defined exactly what those limits are. More importantly, Turing proves that his abstract machine, simple as it is, can compute anything that's computable, that any algorithm executable on any computing device can be executed on a Turing machine given enough time and memory. This universality means that thinking about computation in the abstract, separate from physical machines, is meaningful. Computation is a mathematical concept with precise properties, not just engineering. War arrives. You find yourself at Bletchley Park, 1940s, the country estate converted to code-breaking facility, where Turing and others work on breaking German Enigma codes. The atmosphere is urgent. Cold buildings in winter, blackout curtains, exhausted workers analysing intercepted messages. The machines they build to assist code breaking are electromechanical, clicking and whirring, bronze wheels and relays, the bomb machines that test possible Enigma settings, rejecting impossibilities faster than humans could. The work is intellectual, but the machines assist, performing the mechanical parts of cryptanalysis, testing combinations, finding contradictions. This is applied computation on an industrial scale, machines following logical rules to solve problems that matter existentially. The machines don't think in any deep sense, but they perform tasks that require intelligence when humans do them. The boundary between tool and mind blurs slightly. The smell is of electrical equipment running hot, metal and ozone the ever-present cigarette smoke of the era. The sounds are machine clicking, paper rustling, quiet conversations in technical jargon, occasional excitement when a message is broken. Turing moves between mathematical work and machine operation, between pure thought and engineering compromise, seeing how abstract computation manifests in physical devices. After the war, electronic computers become possible. Vacuum tubes replace relays, switching thousands of times per second instead of dozens. Turing works on computer design, thinking about what these machines might do beyond calculation. In 1950, he publishes a paper that will define the field of artificial intelligence before that term exists. Computing machinery and intelligence, asking directly, can machines think? Imagine Turing writing this paper, perhaps in his office, typewriter clacking as he composes arguments. The question, can machines think, is too vague, he argues, depends on defining machine and think precisely, leads to philosophical tangles. Instead, he proposes an operational test. Conduct a conversation with both a human and a machine through text alone. If you can't reliably tell which is which, does it matter whether the machine really thinks? This Turing test, as it becomes known, sidesteps metaphysics for pragmatics. Intelligence might be defined by behaviour rather than internal states. A machine that responds indistinguishably from a human has achieved something significant, whether or not consciousness accompanies it. The paper envisions machines that learn like children, through experience and feedback, adjusting their behaviour based on outcomes. The vision is clear even though implementation remains distant. The philosophical earthquake this creates will reverberate for decades. If thinking is symbol manipulation according to rules, machines can think. But does mere symbol manipulation constitute understanding? Does a machine running a program know what it's doing, or merely execute instructions blindly? Philosophers will debate this endlessly, the Chinese room argument and its counters, consciousness and intentionality and qualia. The questions remain alive today, never satisfactorily resolved. Meanwhile, actual computers are being built. You find yourself now in university basements and military research facilities, 1940s and 1950s, standing before room-sized machines that are simultaneously magnificent and primitive. ENIAC, UNIVAC, early computers whose names we remember primarily as milestones. The rooms are warm, almost hot, from vacuum tubes generating heat like small furnaces. The smell is of hot electronics, that distinctive scent of electrical components at operating temperature, metal and dust, and warming insulation. The machines fill rooms, rows of metal cabinets containing thousands of vacuum tubes, each tube a glass envelope glowing when powered, switching on and off, creating the electronic logic that performs computation. The sound is a constant hum, cooling fans, moving air, the occasional click of relays, printers clattering when output is produced. The light is warm, a combination of overhead fluorescence and the glow from tubes visible through front panels, amber and orange. Operating these computers requires specialists. Programmers write code, though not as we know it now, often wiring patch cables to set up problems, or preparing programs on paper tape or punch cards. The cards are physical objects, stiff cardstock with rectangular holes punched in patterns, handled carefully because creased or torn cards cause errors. The tactile reality of programming, boxes of cards representing programs, the weight of a program measured in pounds. The punch cards themselves have a history, descended from Jacquard loom cards, the same technology Ada Lovelace imagined for the analytical engine. Each card holds 80 characters typically, punched holes representing data or instructions through their presence or absence in specific positions. The cards accumulate in boxes, organised in decks that must maintain exact order, dropped decks causing disasters, requiring hours to reorganise and reorder. Some programmers draw diagonal lines across deck edges with coloured markers, making dropped cards easier to reorder by matching the line. The key punch machines that create these cards are themselves specialised devices, mechanical typewriters that punch holes instead of printing ink. Operators, often women in this era, transcribe coding sheets to cards, typing rapidly, the machines clattering rhythmically, stacks of blank cards feeding through, punched cards accumulating in output hoppers. The work requires accuracy. Errors mean new cards must be punched, and finding errors in card decks during program execution is tedious. The card readers that feed programs into computers are mechanical marvels, reading hundreds of cards per minute, sensing holes through mechanical pins or light sensors, converting patterns to electrical signals. The readers are temperamental, jamming on bent cards, misreading dirty cards, requiring regular maintenance. Operators develop sixth senses for impending problems, recognizing slight changes in sound or rhythm that presage jams, ready with tools to clear stuck cards without tearing them. The ritual of running a program involves preparation and waiting. Programmers write code during daylight hours, translating algorithms into machine instructions, recording on coding sheets. Key punch operators convert sheets to punch cards, creating decks that represent programs. The decks are submitted to computer operators who schedule them, load them into card readers, run the programs in batch, collect printouts. The programmer returns hours or days later to retrieve results, reads through paper output looking for errors or results, debugs, creates new card deck, resubmits. This cycle is slow but accepted as normal. Computers are rare, expensive, shared resources. Getting computer time requires justification, scheduling. Programs run once per day at best, often less frequently. The pace of development is measured in iterations per week rather than per minute, each run precious, each bug requiring another day to fix. Patience is mandatory. The batch processing system imposes discipline. Programmers must think carefully before submitting jobs, mentally executing code to catch obvious errors, because each submission might not run until tomorrow, and mistakes mean another day lost. Debugging becomes an exercise in deduction from limited information, reading printouts to infer what happened inside the computer, reconstructing execution paths from output and error messages, making hypotheses about bugs without ability to interactively examine program state. The printouts themselves are artifacts of the era, fanfold paper emerging from line printers, green and white striped paper with holes along edges for tractor feeds, characters printed in dot matrix or fixed width fonts. Programmers learn to read these outputs expertly, spotting patterns that indicate specific types of errors, recognizing when output format is wrong even if values appear superficially correct. The printouts accumulate in boxes, documentation of attempts that mostly failed, occasionally succeeded, together forming the history of a program's development. Early attempts at AI begin in this environment. Arthur Samuel creates a checkers program that learns from experience, playing thousands of games against itself, adjusting evaluation functions based on outcomes. The program improves gradually, eventually playing respectably, though not achieving mastery. The learning is real but limited, pattern matching without deep understanding. Logic Theorist, created by Newell, Shaw and Simon, proves mathematical theorems, searching through logical derivations, finding proofs of theorems from Principia Mathematica. The proofs are valid, the logic sound, intelligence demonstrated through problem solving. Yet the methods are brute force search with heuristics, not the insight mathematicians use. The boundary between clever algorithm and true intelligence remains unclear. The Dartmouth Conference in 1956 brings researchers together, coining the term artificial intelligence, setting ambitious goals. The proposal suggests that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. The optimism is genuine, based on early successes and the belief that intelligence is computation, reducible to algorithms implementable in software. You watch researchers at this conference, young and energetic, convinced they're on the threshold of breakthrough. John McCarthy, Marvin Minsky, Claude Shannon, others whose names will define the field. They propose a summer project, expecting significant progress in months. They propose the underestimation is enormous but honest. No deception, just the classic programmer's optimism that problems are simpler than they prove to be. The decades that follow will alternate between excitement and disappointment, funding surges and cuts, predictions that AI is imminent, and lamentations that it's impossible. But we're still in the optimistic phase, late 1950s, and a remarkable machine is about to be built. Imagine you now stand in Cornell Aeronautical Laboratory, 1958, watching Frank Rosenblatt work on the perceptron. This is not just software, but a physical device, a room-sized machine, with photocells arranged in a grid, wires connecting them to adjustable weights implemented as electric motors with potentiometers, the whole system designed to learn pattern recognition from examples. The Mark I. Perceptron is impressive in its physicality, the embodiment of a learning algorithm in vacuum tubes and motors. The photocells detect light patterns, simple images projected onto them. The connections between input and output have strengths, weights, adjustable by the motors. During training, examples are shown, correct outputs are specified, and if the perceptron's output is wrong, the weights adjust automatically to reduce error. Repeat thousands of times, and the machine learns to recognize patterns it was never explicitly programmed to detect. This is revolutionary in concept, learning from data rather than programming rules explicitly. Show the machine many examples of letter A and non-A, and it learns to classify new examples. The learning is mechanical, gradient descent on an error surface, but it's genuine adaptation based on experience. Rosenblatt is excited, perhaps overly so, predicting machines that will be able to recognize speech, translate languages, surpass human cognitive abilities. You watch training sessions, repetitive and patient. Examples are shown one by one, motors adjust weights, accuracy gradually improves. The process is slow, mechanical, visible in the physical movement of potentiometers, audible in the hum of motors. Hours of training for tasks that remain simple, recognizing basic shapes, distinguishing patterns. But the principle is sound, the approach fundamentally different from rule-based programming. Each training example requires several steps. Display the pattern on photocells. The input propagates through weighted connections to output units. The output is compared to desired output, error is calculated, weights adjust in proportion to error and input activation. The process repeats for the next example. Thousands of examples must be presented, cycling through the training set multiple times, weights gradually converging to values that minimize classification error. The convergence is not guaranteed to be fast or smooth. Sometimes accuracy improves steadily, error decreasing monotonically. Other times accuracy fluctuates, improving then worsening as weights overshoot optimal values before settling. The training process requires patience, monitoring accuracy after each epoch through the data, deciding when to stop training before the perceptron overfits to training examples, and loses ability to generalize to new patterns. The physical reality of the Mark I. Perceptron creates constraints modern software implementations don't face. The motors adjusting weights have limited precision and speed. The photocells have noise and varying sensitivity. The electronics drift with temperature. These imperfections mean the perceptron's behavior is somewhat unpredictable, not perfectly reproducible. The physical instantiation introducing randomness that might be helpful or harmful depending on circumstances. Rosenblatt documents the training process carefully, recording accuracy curves, analysing which patterns are learned quickly versus slowly, investigating what happens when the training set changes. The methodology is scientific even when technology is primitive, establishing principles that will survive long after the physical perceptron is dismantled and forgotten. The idea that machines can adjust their behaviour through experience, learning from mistakes, improving through practice, this insight transcends the specific implementation. The perceptron captures imaginations, featured in news articles, discussed at conferences, but limitations emerge quickly. The single-layer perceptron can only learn linearly separable patterns, cannot solve XOR and similar problems that require non-linear decision boundaries. Minsky and Papert proved these limitations mathematically in 1969, showing precisely what perceptrons cannot learn. The result dampens enthusiasm for neural networks, contributes to funding cuts, redirects research towards symbolic AI, but the seed is planted. The idea of learning from data, adjusting parameters through training, will survive the coming decades of neglect, waiting for computers powerful enough to train deeper networks. Remember those clerks calculating by hand in counting houses? Now machines can learn to recognize patterns through examples, adjusting internal weights automatically, performing a type of learning that humans do intuitively. The connection between human and machine intelligence grows less clear as machines demonstrate abilities that seem cognitive even if the mechanisms differ. The 1960s see AI research expanding and diversifying. Programs solve algebra problems, manipulate symbolic expressions, prove theorems. ELIZA, created by Joseph Weizenbaum in 1966, simulates a Rogerian psychotherapist responding to typed input with questions and reflections. The implementation is simple pattern matching, no understanding, yet some users become emotionally engaged, confiding in the program, convinced it understands them. The program is elegant in its simplicity, using templates and keywords to transform user statements into questions. If you say, "I am sad," Eliza might respond, "Why do you think you are sad?" Or, "How long have you been sad?" Following patterns that mimic therapeutic conversation without requiring any understanding of emotions or psychology. The illusion works because Rogerian therapy is already non-directive, reflecting statements back to patients, creating Kong-Jian for them to explore their own thoughts. Users type at terminals, seeing their words echoed on the screen. Eliza's responses appearing after brief delays while the pattern matching executes. The interaction feels conversational, the medium itself lending authenticity despite the mechanical nature of responses. Some users, knowing Eliza is a program, still find themselves confiding in it, the therapeutic framing overcoming their knowledge of its artificial nature, the desire to talk overriding skepticism about whether the listener understands. Weizenbaum is disturbed by this, writes about the illusion of understanding, the danger of mistaking programmed responses for genuine intelligence. Eliza demonstrates both promise and peril. Machines can simulate aspects of intelligence convincingly enough to fool users, but the simulation is shallow, processing words without meaning. The gap between appearing intelligent and being intelligent seems vast. Vision systems attempt to interpret images, robots with cameras trying to recognize objects, stack blocks, navigate spaces. The work is difficult, pattern recognition more complex than anticipated. Early systems work only in carefully controlled environments, toy worlds with clean lighting, distinct objects, constrained possibilities. Real-world vision with variable lighting, occlusions, ambiguity remains beyond reach. Natural language understanding proves similarly difficult. Parsing sentences structurally is achievable, but extracting meaning requires knowledge about the world that resists formalization. The sentence, "The trophy wouldn't fit in the suitcase because it was too large," requires understanding physical objects, size relationships, pronouns references, common sense reasoning. AI systems stumble on examples that humans understand effortlessly. You observe researchers in labs, MIT AI Lab, Stanford AI Lab, Carnegie Mellon, the Centers of Activity, graduate students working late, debugging code, running experiments, discussing results. The atmosphere is collaborative but competitive, different research groups pursuing different approaches, hoping their method will achieve the breakthrough. The smell is coffee and dry erase markers, old electronics and photocopied papers. The sound is keyboards clicking, printers whirring, animated conversations about algorithms and representations. The labs themselves have character developed through years of accumulation. Whiteboards cover walls, filled with equations and diagrams that persist for weeks or months, erased reluctantly when space is needed for new ideas. Bookshelves hold technical references, conference proceedings, dissertations bound in library bindings. Desks are cluttered with papers, printouts, technical manuals, coffee cups accumulating until cleaning drives happen periodically. The computers, still large but no longer room-filling, sit in machine rooms with raised floors for cable management, operators monitoring them through windows. The people form a community, recognizing each other at conferences, collaborating and competing, reviewing each other's papers, arguing about approaches. Graduate students work for years on dissertation projects, some succeeding spectacularly, most contributing incremental progress, a few failing to produce results and leaving with master's degrees instead of PhDs. The attrition is high, the problems are difficult. Success requires combination of intelligence, persistence, and luck in choosing tractable problems. The daily routine of research involves reading papers over morning coffee, trying to understand what others have done, looking for ideas to build upon or mistakes to avoid. Then hours of implementation, translating algorithmic ideas into code, debugging when the implementation doesn't match the theory, which is frequently. The computer time is still precious, shared among researchers, scheduled in blocks. An afternoon might involve preparing a job to run overnight, checking results the next morning, debugging and preparing another run, the cycle repeating until something works or the approach is abandoned. Lab meetings provide structure, weekly gatherings where researchers present their work, receive feedback, discuss challenges. The senior professor guides discussion, suggests directions, reminds people of relevant prior work, helps unstuck students who've been struggling for weeks. The meetings are intellectual, but also social, maintaining cohesion in groups where individuals might otherwise work in isolation, ensuring knowledge is shared rather than siloed. Funding flows from military agencies, DARPA, supporting research that might have defense applications. The money enables labs to acquire expensive equipment, hire researchers, sustain years of work on difficult problems. The grant applications promise progress, outline ambitious goals, justify continued investment. Some promises are met, most are delayed, the timeline forever several years away for human-level AI. The optimism of the era is genuine, but will prove premature. The problems are harder than they appear, intelligence more complex than early researchers appreciated. The symbolic AI approach, representing knowledge as logic and rules, scaling up toward intelligence through better knowledge representation, will hit limits. The combinatorial explosion of possibilities in realistic domains, the difficulty of capturing common sense in formal rules, the brittleness of systems that fail when encountering unexpected situations. But these problems aren't yet apparent in the 1960s. Researchers see successes in constrained domains, extrapolate to general intelligence, believe the path is clear even if long. Conferences are optimistic, papers describe progress, the field is young and energetic, problems seem solvable through more research, better algorithms, faster computers. The computers themselves are getting smaller and faster, though still large by modern standards. Transistors replace vacuum tubes, reducing size and power consumption, increasing reliability. Mainframes fill rooms, but the rooms are smaller, the heat less intense. Magnetic core memory provides kilobytes of storage, expensive but reliable. Disk drives store megabytes, massive platters spinning in sealed units, revolutionary compared to punch cards and tape. Programming becomes more abstract, high-level languages like Fortran and Lisp, allowing algorithms to be expressed in human-readable form, compiled to machine code. The gap between thought and implementation narrows. Lisp becomes the language of AI research, designed for symbolic manipulation, list processing, recursion. The elegance of Lisp code, defining algorithms that manipulate symbols, feels closer to thought than machine instructions ever did. Lisp, invented by John McCarthy in 1958, is revolutionary in its simplicity and power. The syntax is uniform, everything is either an atom or a list enclosed in parentheses. Functions and data have the same representation. Code can manipulate code as data. This homoiconicity, the property that code and data are indistinguishable, enables metaprogramming, programs that write or modify programs, a capability that seems almost magical compared to conventional languages. The garbage collection in Lisp, automatic memory management that reclaims unused memory without programmer intervention, removes a major source of errors and tedium. Programmers can allocate memory freely, building complex data structures without tracking what needs to be freed. The runtime system handles this automatically, though at cost of occasional pauses when garbage collection runs, pauses that are acceptable trade-off for the programming convenience. Lisp's read, eval print loop, the interactive environment where expressions can be typed and immediately evaluated, enables exploratory programming, testing ideas incrementally, building programs bottom-up from tested components. This interactive development style is foreign to batch processing, but natural for AI research, where algorithms are often discovered through experimentation rather than designed fully in advance. But the fundamental barrier remains. Intelligence is not just symbol manipulation. Or perhaps it is, but the symbols need grounding, connection to meaning that formal systems lack. The Chinese room argument, though not formulated until later, captures the intuition. A system that manipulates symbols according to rules without understanding what the symbols mean is not truly intelligent, is executing syntax without semantics. You watch the decade close with AI still promising but undelivered, research continuing, optimism undiminished but untested. The challenges ahead are not yet visible, the coming period of reduced funding and skepticism still years away. For now, AI research is vibrant, the field young. The researchers convinced they're building the future, one algorithm at a time. The story continues, but rest comes easier knowing the work persists. Researchers continuing to experiment, programs running through the night, data being processed, results analysed. Tomorrow more experiments will run, more papers will be written, more progress will accumulate. The rhythm of research continuing regardless of funding cycles or public attention. The question Turing asked remains open, the search for machine intelligence ongoing, patient and methodical, one insight building on another, slowly approaching understanding of both artificial and natural intelligence. Decades have passed, carrying you forward into the 1970s and 1980s, an era that will later be called the AI winter, though the term suggests a drama that doesn't match the quiet reality of labs continuing work with reduced resources. You find yourself in research facilities where the optimism of the 1960s has cooled, funding committees more sceptical, progress slower than promised, the field entering a period of reduced expectations and limited growth. The change isn't sudden, no specific moment when winter arrives, just gradual cooling as grants become harder to obtain, research groups shrink, some labs close. The disappointment stems from over-promising early researchers predicting human-level AI within years or decades, not appreciating the complexity of intelligence, the difficulty of replicating in silicon what biological brains do effortlessly. Natural language understanding proves harder than expected. Vision systems fail outside controlled environments. The combinatorial explosion of possibilities in realistic problems overwhelms approaches that worked in toy domains. You watch a researcher defending his grant proposal to a review committee, explaining why AI research should continue despite missed predictions. The conference room is institutional, fluorescent lights overhead, government officials sitting around a table with proposal documents, asking pointed questions about deliverables and timelines. The researcher explains that progress is happening, shows demos of systems that work in limited domains, argues that fundamental research takes time, breakthroughs can't be scheduled. But the committee has heard similar arguments before, funded similar promises, needs results, not potential. The funding is reduced, enough to continue, but not to expand, a vote of limited confidence. Labs adjust to the new reality. Equipment is used longer, maintained carefully because replacements aren't budgeted. Graduate students take longer to complete degrees because computer time is more limited. Experiments must be prioritized, some investigations abandoned as too expensive to pursue. Faculty teach heavier course loads to justify positions, spending weekends on research that was once their full-time focus. The pace slows but doesn't stop, patient researchers continuing because the questions still matter, the problems still fascinate, even if solving them takes longer than expected. The atmosphere in labs during this period is muted but persistent. Researchers gather for lab meetings, discuss papers, present results, but the excitement is tempered by awareness that breakthroughs are rare. Most work is incremental, papers are read by small communities. Conferences become smaller, attendance drops as travel budgets shrink. The same familiar faces appearing year after year, a community that hasn't grown but persists. The technology itself continues advancing, though not in ways that immediately help AI. Computers get faster, following Moore's law, transistor counts doubling every 18 months to 2 years. Mainframes become more powerful. Mini-computers bring computation to departments that couldn't afford mainframes, and the first personal computers appear, though these are still too limited for serious AI work. Memory capacity grows, kilobytes becoming megabytes. though even megabytes are insufficient for the complex models researchers envision. The theoretical work continues, perhaps even accelerates during this period, researchers focusing on foundations when practical applications stall. Neural network theory advances, though implementations remain impractical. Backpropagation, an algorithm for training multi-layer neural networks, is developed and rediscovered several times during the 1970s and 1980s, each time remaining a theoretical curiosity because computers aren't fast enough to make it practical for networks of useful size. You find yourself reading papers from this era, published in specialized journals, circulated in technical reports, sometimes photocopied and shared informally because the publishers don't expect wide readership. The papers are mathematically dense, proofs and theorems, establishing properties of learning algorithms, proving convergence under certain conditions, analyzing computational complexity. The work is rigorous but abstract, building theory that will later support practice, though the lag between theory and application is measured in years or decades. The backpropagation algorithm itself is elegant in hindsight, almost obvious once understood, yet its development took multiple discoveries by different researchers, the ideas circulating slowly through the community. The algorithm allows neural networks with hidden layers to learn, the gradient of error with respect to weights calculated by propagating error backwards through the network, hence the name. Hidden layers enable learning non-linear functions, overcoming the perceptrons' limitations, but training requires computing gradients through all layers, a computationally expensive operation that's only feasible with faster computers and efficient implementations. Meanwhile, a different AI approach is flourishing. Expert systems, rule-based programs that encode human expertise in specific domains. These systems avoid learning entirely, instead capturing expert knowledge as if-then rules, hundreds or thousands of them, representing how experts reason about problems. The approach has advantages during the AI winter, promising practical applications without requiring breakthroughs in learning or understanding, delivering value with current technology. You find yourself in an office building where an expert system is being developed, perhaps the mid-1980s, watching knowledge engineers work. These are specialists in extracting expertise from human experts and encoding it as rules, an occupation that exists briefly during this era before fading when the approach's limitations become clear. The knowledge engineer interviews a doctor about diagnosing blood infections, recording how the doctor reasons through cases, what symptoms suggest which infections, how lab results modify probabilities, the decision trees that experienced clinicians follow. The sessions are challenging. The doctor knows how to diagnose, but explaining the reasoning is difficult. Much of the expertise is intuitive, learned through experience, difficult to articulate as explicit rules. The knowledge engineer asks probing questions, presents hypothetical cases, tries to extract the rules underlying the doctor's decisions. The process is slow, weeks of interviews to capture expertise that the doctor applies in minutes, the translation from intuitive to explicit understanding requiring patient work. The interviews are recorded, transcribed, analysed. The knowledge engineer reviews transcripts looking for patterns, decision trees that the doctor follows, cases where the reasoning is clearest. The doctor might say, "When I see these symptoms together, I think of this infection first, but if the lab results show this pattern, I reconsider and think of these alternative infections." The knowledge engineer translates this to conditional rules. If symptoms X and Y and Z, then suspect infection. A with confidence 0.8. If lab results show pattern P, then reduce confidence in A and increase confidence in B and C. But the process is never complete. For every rule extracted, exceptions and special cases emerge. The doctor mentions that the rule doesn't apply to patients with certain comorbidities or to patients taking specific medications or in specific clinical settings. Each exception requires additional rules, the complexity growing as edge cases are handled, the rule base expanding from dozens to hundreds to thousands of rules, each one dependent on others, the interactions between rules becoming difficult to predict. Testing the system reveals gaps in the knowledge base. Cases that the doctor would handle easily cause the system to fail, not because the rules are wrong, but because necessary rules are missing, the knowledge acquisition incomplete. The knowledge engineer returns to the doctor, presents the failing cases, extracts additional rules, the cycle repeating until the system handles the test cases adequately. But new cases always reveal new gaps, the knowledge acquisition theoretically endless, practically limited by time and budget. The rules themselves are encoded in specialized languages, computer programs, but unlike traditional code, declarative statements of conditions and conclusions rather than procedural instructions. A rule might state, if patient has fever and white blood count is elevated, an organism cultured from blood is gram-positive cocci. Then infection is probably staph infection with confidence 0.7. The system chains such rules together, reasoning from symptoms to diagnoses, combining evidence, managing uncertainty through numerical confidence factors that update as more information becomes available. The environment where these systems are built is different from research labs, corporate offices rather than universities, commercial development rather than academic exploration, deadlines imposed by customers rather than the patient timeline of research. The smell is office coffee and dry marker boards. The sound is meetings and keyboards clicking, photocopiers running, telephones ringing. The dress code is business casual rather than the casual dress of research labs. The language is deliverables and milestones rather than hypotheses and experiments. The expert systems are deployed in some cases used for actual decisions, though carefully supervised. Mycin, developed at Stanford for diagnosing blood infections, achieves accuracy comparable to human experts in controlled studies, sometimes outperforming junior doctors. But it's never used clinically. Legal and liability concerns preventing deployment. The question of who is responsible when a computer system makes a wrong diagnosis that harms a patient proving unanswerable in the era. The technical achievement is real, but the social challenges of deploying AI in high-stakes decisions remain unsolved. The evaluation studies for Mycin are careful and rigorous, comparing the system's recommendations to those of human experts, using blind evaluations where reviewers don't know whether recommendations came from Mycin or humans. The system performs well, sometimes better than doctors with limited experience in infectious diseases, comparable to specialists. The knowledge base encodes expertise acquired over years of clinical practice, rules representing diagnostic patterns that experts use, combined with an inference engine that chains through rules, managing uncertainty through mathematical certainty factors. But deployment faces obstacles beyond technical performance. Doctors are legally and professionally responsible for patient care, liable for errors, required to exercise judgment. Using a computer system's recommendations doesn't transfer that responsibility, so doctors using Mycin would still need to verify its reasoning, understand why it recommended particular treatments, effectively making them supervisors of the system rather than users. This defeats the purpose of automation, doesn't reduce workload sufficiently to justify the effort of maintaining the system. The liability concerns are profound in medical applications. If mycin recommends a treatment that harms a patient, who is responsible? The programmer who wrote the code? The knowledge engineer who encoded the rules? The doctor who followed the recommendation? The hospital that deployed the system? Medical malpractice law, developed for human decision-making, doesn't clearly apply to AI systems, creating legal uncertainties that discourage adoption even when technical capabilities are adequate. Dendral identifies molecular structures from spectroscopy data used successfully in chemistry, published in peer-reviewed journals, a practical AI success. R1, later renamed XCon, helps configure computer systems for Digital Equipment Corporation, saving millions by automating a complex task that previously required expert configurators. These successes show expert systems can deliver value, that AI has practical applications, that the field isn't purely academic speculation, but the limitations emerge gradually. Expert systems are brittle, failing catastrophically when encountering situations outside their rule base, unable to handle novel cases the way human experts can. The knowledge acquisition bottleneck proves severe. Building rule bases requires enormous effort. Experts struggle to articulate their reasoning. Subtle exceptions and special cases proliferate. Maintaining systems as domains evolve requires constant updates. The promise of capturing expert knowledge fades as the difficulty of capturing becomes apparent. You observe the life cycle of an expert system project, from initial enthusiasm through deployment to eventual retirement. The first months involve interviews and rule encoding, the system growing gradually, tested against known cases, accuracy improving as more rules are added. Deployment is careful, the system used alongside human experts, recommendations reviewed before being acted upon, errors caught and added to test suites. For a while the system is useful, handling routine cases, freeing experts for difficult problems. But maintaining the system becomes burdensome. As the domain changes, new medications become available, new diagnostic tests, new pathogens. The rules must be updated. The original knowledge engineers have moved to other projects. New maintainers must understand the rule base, but the rules have grown tangled. Interactions between rules creating unexpected behaviours. Adding new rules sometimes breaks existing ones. The system becomes legacy code, difficult to modify, eventually replaced by newer approaches, or simply discontinued. Remember Rosenblatt's perceptron learning from examples? The idea survived this quiet period. The theoretical foundations were being laid, waiting for computers powerful enough to make neural networks practical again. The patient accumulation of understanding, theoretical work during years when practical implementation was impossible, building the knowledge base that would enable the next wave. The computers themselves are transforming during this period, though the transformation is gradual enough that individual years don't seem revolutionary. The mainframes of the 1970s give way to mini-computers, then to personal computers, the IBM PC arriving in 1981, Apple Macintosh in 1984, machines with graphical interfaces accessible to individuals, though still limited by current standards. A PC might have 640 kilobytes of memory, a few megabytes of hard disk storage if you could afford one, processor speeds measured in megahertz. Powerful enough for word processing and spreadsheets, barely adequate for the simplest neural networks. The culture of computing changes with personal computers. No longer is programming something done at terminals connected to shared mainframes, submitted as batch jobs, results returned hours later. Now you have a machine on your desk, immediate feedback, the ability to iterate rapidly, programming languages that compile in seconds rather than minutes. The democratization of computing, access spreading from specialists to enthusiasts, hobbyists programming in basements, the birth of software industry, companies forming around programs rather than hardware. But for AI research, personal computers are toys, too limited for serious work. The neural networks researchers envision, with hundreds or thousands of neurons, millions of connections, require computational power beyond what desktop machines can provide. The research continues on workstations and mini-computers, university machines shared among researchers, computation still a limited resource requiring careful rationing. You find yourself in a graduate student's life during this era, perhaps at MIT or Stanford or Carnegie Mellon, the top AI programs. The student arrives at the lab in late morning, mornings being difficult after late nights coding. The lab is in a university building, worn furniture, whiteboards covered with equations that accumulate over weeks, desks cluttered with papers and empty coffee cups, computers humming, the familiar environment of academic research. The day starts with reading, catching up on papers, seeing what other research groups have published, understanding the current state of the field. The papers arrive by mail, physical journals and technical reports, photocopied and passed around, or found in the library, the system slow but adequate. Reading is essential, understanding what's been tried, what worked, what failed, building on others' work rather than rediscovering what's known. Then implementation, translating algorithmic ideas into code, usually in Lisp or increasingly in C, the tension between elegance and efficiency, Lisp's ease of expression versus C's speed. The coding happens in editors on text terminals, green or amber text on dark screens, or in the newer Lisp machines, specialized workstations optimized for running Lisp efficiently. The development cycle is edit, compile, run, faster than batch processing, but still requiring patience, compilation taking minutes, runs taking longer, debugging by adding print statements, and rerunning. The code represents ideas, attempts to solve problems, implementations of algorithms described in papers. Most attempts fail or produce disappointing results. The problems are hard. The approaches are experimental. Success is rare. But occasionally something works, accuracy improves, the program learns a pattern or solves a problem, and those moments of success justify weeks of failures, providing encouragement to continue, evidence that progress is possible. Lab meetings provide structure and community, weekly gatherings where students present their work, receive feedback from advisor and peers, discuss challenges, brainstorm solutions. The meetings are collaborative, people genuinely trying to help each other, suggesting relevant papers, pointing out bugs in reasoning, proposing alternative approaches. The academic culture, at least in good labs, is more cooperative than competitive within the group, rivalry reserved for other universities, everyone locally working toward shared goals of advancing the field. Conferences are highlights, annual or semi-annual gatherings where the community meets, presents papers, sees what others are doing, networks and socializes. The student submits a paper, waits nervously for reviews, celebrates acceptance or processes rejection, attends the conference to present, stands nervously through question sessions, attends other talks, meets famous professors whose papers they've read, stays up late talking with other students about research, returns energized or discouraged depending on how the conference went. The timeline for graduate school is long, 5 to 7 years typical, sometimes longer. The first years involve coursework, learning foundations, reading breadth of literature, passing qualifying exams. Then the dissertation research, finding a problem, attempting approaches, failing, trying alternatives, gradually converging on something that works well enough to graduate. The dissertation itself is a book, hundreds of pages, describing the problem, related work, the approach, experimental results, conclusions. Writing it is exhausting, the final push to completion after years of effort. Life beyond research is minimal during graduate school. The stipend is modest, enough to survive but not thrive. Students living in cheap apartments, eating cheap food, their social lives revolving around the lab and other students in similar situations. Weekends are spent in the lab if research is going well, or avoided if it's going poorly and mental break is needed. The boundary between work and life blurs, research being both job and passion, consuming in ways that 9-to-5 jobs aren't. The 1980s end with AI still promising, but largely undelivered, expert systems having had their moment of commercial success, but their limitations becoming apparent, neural networks still waiting for computational power that makes them practical. But the foundations are in place, the theory developed, the researchers trained, waiting for the next wave. The quieter years weren't unproductive, though progress was less visible than during boom periods. The theoretical understanding deepened, new algorithms were developed, communities were maintained, students were trained, the infrastructure of AI research persisted. When the next boom arrived, the field was ready, the knowledge accumulated during quiet years enabling rapid progress once conditions allowed. You watch the decade turn, 1990 arriving, personal computers becoming more powerful, 486 processors running at tens of megahertz, memory measured in megabytes, not kilobytes, hard drives holding hundreds of megabytes. Not yet sufficient for large neural networks, but approaching usability, the gap between what researchers envision and what's computationally feasible narrowing. The internet is spreading, slowly connecting universities, enabling collaboration and communication that was previously difficult. Email replaces postal mail for paper distribution. FTP allows sharing datasets and code. Discussion groups enable conversations among researchers who've never met in person. The pace of research accelerates, ideas spread faster, replication becomes easier, the infrastructure for rapid progress is being built. Graphics processing units, GPUs, are emerging, designed for video games, dedicated to rendering 3D graphics rapidly. The computational pattern they optimize, matrix multiplications and parallel operations, happens to match what neural networks require. This coincidence won't be fully exploited until later, but the technology is developing, waiting for someone to recognize its potential for AI. Remember those clerks doing arithmetic by hand, questioning whether machines could think? Now the machines can calculate millions of times faster, store millions of times more information, but true machine intelligence remains elusive, the gap between computational power and intelligence proving larger than early researchers imagined. The question is shifting from can machines think to how much computation is required for thinking, and the answer remains uncertain. The research continues, patient and persistent, experiments running overnight, papers being written, conferences being held, students graduating and joining the field or leaving for industry. The rhythm of research, now decades old, is established, the field mature enough to continue regardless of funding cycles or public attention. AI has become a permanent part of computer science, no longer speculative but established, even if the grandest goals remain distant. The story continues, but rest comes easier, knowing the work persists, the patient accumulation building towards something, even if what that something will be remains unclear. Tomorrow more experiments will run, more papers will be published, more students will debug code late at night, the rhythm continuing, slow and steady, approaching understanding one small insight at a time. Generations pass. You now find yourself in the late 1990s, and early 2000s, standing at the threshold of a transformation that won't be recognized as revolutionary until years later. Neural networks are returning from the shadows, enabled by computers that have finally become fast enough to train networks of useful size. The theoretical work done during the quieter years is ready to be implemented, backpropagation algorithm waiting to be applied at scale, researchers ready to experiment with deeper networks now that computational constraints are easing. The computers enabling this are diverse. University labs have workstations, Sun or Silicon graphics machines, powerful by standards of the era, though primitive compared to what's coming. Graduate students have desktop PCs, Pentium processors running at hundreds of megahertz, gigabytes of storage, enough memory to run meaningful experiments. The software infrastructure is maturing, libraries for neural network implementation appearing, researchers sharing code through early internet forums and FTP sites. But the real transformation comes from an unexpected source: graphics cards. GPUs, designed for rendering video game graphics, are becoming increasingly powerful, processing millions of pixels per frame at dozens of frames per second, performing matrix operations in parallel with hundreds of small processors. A researcher named Ian Book notices in the early 2000s that these operations resemble what neural networks require, that the same hardware designed to calculate lighting and textures could calculate neural network forward and backward passes. The recognition comes gradually. GPUs are structured around performing the same operation on many data elements simultaneously, SIMD parallelism, exactly what matrix multiplication requires. A neural network layer's forward pass is essentially multiplying an input vector by a weight matrix, an operation that can be parallelized across GPU cores. The backward pass, calculating gradients, is similar mathematics, matrix multiplications with transposes, equally parallelizable. The graphics APIs of the era, OpenGL and DirectX, are designed for rendering, not general computation. Programming GPUs for neural networks requires encoding matrix operations as graphics operations, pretending to render triangles or apply texture mappings while actually performing arithmetic. The programming is awkward, requiring creative misuse of graphics features, debugging difficult because graphics drivers aren't designed for scientific computing and produce cryptic errors when used in unexpected ways. But researchers persist because the speed-ups are enormous. A GTX 280, a high-end GPU from 2008, can perform hundreds of billions of floating-point operations per second, an order of magnitude more than CPUs of the era. Matrix operations that take hours on CPUs finish in minutes on GPUs. The constraint shifts from compute time to memory bandwidth. Moving data to and from GPU memory becomes the bottleneck, requiring careful optimization of memory access patterns. The insight spreads slowly through the community. GPUs are gaming hardware, not scientific equipment. Using them for computation requires programming in graphics APIs, treating neural network operations as if rendering images, a conceptual mismatch that makes implementation awkward. But the speed improvement is dramatic, 10 or 100 times faster than CPUs, enough to make experiments that were impractical suddenly feasible. You watch a researcher in the mid-2000s, perhaps at University of Toronto or New York University, setting up GPU computation for neural networks. The programming is difficult, writing code that pretends to render images but actually performs matrix multiplications, debugging by checking that GPU results match CPU results on small examples, optimizing memory access patterns to maximize GPU utilization. The process is technical and tedious, but the payoff is enormous. Training that took days on CPUs now taking hours on GPUs. NVIDIA, the GPU manufacturer, eventually releases CUDA, a programming framework that allows using GPUs for general computation without graphics API contortions. The release in 2006 enables more researchers to use GPUs. Libraries emerge, CUDNN, for neural networks. The ecosystem develops. GPU computing becomes accessible to researchers without graphics programming expertise. The computational barrier that limited neural networks for decades is finally falling. Datasets are growing simultaneously. The internet has made collecting large datasets easier. Images and text scraped from websites. Volunteers contributing labeled data through crowdsourcing platforms. Academic datasets shared freely. ImageNet, assembled starting in 2009, contains over 1 million images across thousands of categories, each image manually labelled, a scale unimaginable in earlier eras. The dataset will become crucial for training and evaluating computer vision systems. The combination of faster computers, especially GPUs, and larger datasets enables training deeper networks. Researchers experiment with networks having not just 3 or 4 layers like earlier work, but tens of layers, hundreds of layers in later years. The depth enables learning hierarchical representations, early layers detecting simple features, edges, colours, middle layers combining these into textures and parts, late layers representing objects and concepts. The hierarchical structure emerges through training, not programmed explicitly, discovered by the network through exposure to data. Jan LeCun's work on convolutional neural networks continues through this period, demonstrating that networks with convolutional layers specialized for image processing can recognize handwritten digits with high accuracy. Banks begin using these networks for reading checks, processing millions of checks, a practical application of neural networks that validates the approach. The success is quiet, not dramatic, checks being processed automatically without public awareness that AI is involved, but it proves neural networks can handle real-world tasks at scale. It proves neural speech recognition improves gradually through neural networks. The hidden Markov models used previously are augmented and eventually replaced by deep neural networks that learn acoustic patterns directly from audio, combined with language models that predict likely word sequences. The accuracy improves year by year, error rates dropping, speech recognition systems moving from barely usable to acceptably reliable, from research curiosities to products deployed in smartphones and virtual assistants. Machine translation, translating between languages, benefits from neural networks starting in the mid-2000s. The statistical machine translation systems used previously based on phrase tables and statistical alignment are replaced by neural machine translation, networks that learn to map sequences in one language to sequences in another. The quality improves dramatically, translations becoming more fluent, handling context better, though still making errors that reveal lack of true understanding. You observe this progress from research labs and corporate research divisions. Google and Microsoft and Facebook establish AI research labs, hiring professors and students, providing computational resources far beyond what universities can afford, publishing research openly while also applying it to products. The boundary between academic and industrial AI research blurs. Researchers moving between university and industry, sometimes holding joint appointments. The distinction between basic and applied research becoming less clear. The researchers themselves are diverse now, Not just computer scientists, but mathematicians, physicists, neuroscientists, engineers, people from varied backgrounds drawn to AI's promise. The field has grown large enough to support specialization, some focusing on theory, others on applications, some developing new architectures, others collecting datasets, some optimizing training procedures, others deploying models in production systems. The ecosystem is rich and complex, no single person understanding all of it, specialization necessary to keep pace with rapid development. The conferences grow larger, attendance in thousands, not hundreds, papers submitted in thousands, with acceptance rates around 20%, competition intense for limited presentation slots. The top conferences, NeurIPS, ICML, ICLR, CVPR, become destinations for seeing cutting-edge work, though the pace of development is so rapid that papers are often outdated by publication, preprint servers enabling rapid dissemination of results before formal publication. Then comes 2012, a year that will be remembered as a turning point. ImageNet holds an annual competition, teams competing to classify images into categories with lowest error rate. The previous year's winners used traditional computer vision approaches, hand-engineered features fed into classifiers, error rates hovering around 25%, improving slowly each year. In 2012, a team from University of Toronto, Geoffrey Hinton's group, enters a deep neural network called AlexNet. The results are announced in September at a workshop associated with the competition. AlexNet's error rate is 15%, nearly half the error of the second-place team, a gap unprecedented in the competition's history. The room reacts with shock and excitement, the magnitude of improvement suggesting something fundamental has changed, that deep learning works at a scale traditional methods cannot match. You watch the presentation, perhaps attending the workshop or viewing it later online. The team, Alex Krzyzewski, Ilya Sutskever, Geoffrey Hinton, present their network architecture. 5 convolutional layers, 3 fully connected layers, 8 layers total, 60 million parameters, trained on ImageNet's million images using 2 GTX 580 GPUs for about a week. The architecture includes several innovations: ReLU activation functions, dropout for regularization, GPU implementation enabling fast training. But mostly it demonstrates that depth and scale, enabled by GPUs and large datasets, produce accuracy improvements that incremental refinements of traditional methods cannot achieve. The impact ripples through the community. Within months, research groups worldwide are re-implementing AlexNet, training their own versions, experimenting with variations, applying similar approaches to other problems. The next year's ImageNet competition is dominated by deep learning entries, error rates dropping further, the transition from traditional to deep learning methods nearly complete. Within a few years, deep learning becomes the dominant approach, not just for computer vision, but for most AI tasks. The paradigm shift is complete. The code for AlexNet is released, enabling others to replicate the results, build upon the architecture, understand the implementation details. The transparency accelerates progress. Researchers don't need to rediscover the architecture from scratch, can start with working code and iterate from there. The culture of sharing code and pre-trained models becomes standard in deep learning. Unlike earlier eras, where implementations were often proprietary or lost when researchers graduated or changed institutions, the pre-trained models themselves become valuable resources. Training. AlexNet from scratch requires computational resources beyond what most research groups can afford, but the trained weights can be shared, downloaded, used as starting points for new tasks through transfer learning. A model trained on ImageNet learns general visual features that transfer to other vision tasks, reducing training time and data requirements for new applications. The practice of sharing pre-trained models becomes standard, democratizing access to powerful models. You observe the aftermath, the flood of papers applying deep learning to everything, the rush to adopt neural networks, sometimes succeeding spectacularly, sometimes failing when problems don't suit the approach, but trying anyway because neural networks are fashionable. The field experiences rapid growth, funding increasing, students flocking to AI programs, companies hiring machine learning engineers, the ecosystem expanding rapidly, perhaps too rapidly, quality sometimes sacrificed to quantity. But the underlying progress is real. Image recognition reaches human-level performance and then surpasses it on specific benchmarks. Object detection in images, semantic segmentation, image captioning, visual question answering, all benefit from deep learning, systems achieving accuracy that seemed impossible years earlier. The vision systems that failed in the 1960s in carefully controlled toy worlds now work reliably in realistic images with variable lighting, occlusions, clutter. The problems that seemed insurmountable now solved, at least for narrow tasks. Remember those early vision systems that could only stack blocks in toy worlds? Now neural networks can identify thousands of object categories in realistic photographs, distinguish between similar objects, handle partial occlusions, work with variable lighting, all through training on large datasets rather than programmed rules. The transformation from programmed intelligence to learned intelligence, from rules to examples, is complete for vision tasks. The training process itself becomes a subject of study and optimization. Researchers develop better optimization algorithms, ADAM RMS prop, better initialization strategies, Xavier He initialization, better regularization techniques, batch normalization, dropout variations, better architectures, ResNet, Inception, DenseNet, the accumulated wisdom of thousands of experiments distilled into best practices that improve training reliability and final accuracy. The computational requirements grow enormous. Training large networks on large datasets requires clusters of GPUs, sometimes hundreds of them, running for days or weeks, consuming megawatt hours of electricity, costing hundreds of thousands or millions of dollars in compute time. The scale excludes smaller research groups who lack resources, concentrating power in well-funded labs at major universities and large companies, raising concerns about democratization of AI research. But the results justify the investment for those who can afford it. Each successive ImageNet winner reduces error rates, new architectures are published, techniques transfer to other domains, the pace of progress accelerates. By 2015, image recognition error rates are around 3%, better than human performance on some measures. The problem that occupied computer vision researchers for decades essentially solved for the narrow task of image classification. The success in vision encourages applying deep learning elsewhere. Natural language processing, the field concerned with understanding and generating text, begins its own deep learning revolution in the mid-2000s, though the techniques require adaptation since text is sequential rather than spatial, words forming sequences rather than grids. Recurrent neural networks, RNNs, and especially their variant long short-term memory networks, LSTMs, become standard for sequence processing, remembering information across time steps, generating text one word at a time, translating sequences from one language to another. But RNNs have limitations, struggling with long sequences, computationally expensive to train because of sequential dependencies preventing parallelization. The breakthrough comes in 2017, a paper from Google titled "Attention is All You Need," proposing the transformer architecture, a network that processes sequences entirely through attention mechanisms, no recurrence, enabling parallel training, scaling to much longer sequences than RNNs could handle. The transformer becomes the foundation for modern natural language processing, enabling models that will transform the field in subsequent years. But that story belongs to the next chapter, the deep learning era's culmination, the moment when learning from data produces systems that not only classify and recognize, but generate and converse. Systems that blur the boundary between pattern matching and understanding, between computation and cognition. The story continues, but rest comes easier, knowing the foundations are laid, the computational barriers overcome, the algorithmic insights discovered, the infrastructure for rapid progress established. Tomorrow more models will train, more papers will be published, more applications will be deployed, the rhythm accelerating but still following the pattern established decades earlier, the patient iteration toward greater capability. You now find yourself in the present era, the 2020s, standing amid an artificial intelligence renaissance that would have seemed like science fiction to the researchers of earlier decades. The transformation that began with AlexNet has accelerated, deep learning spreading across domains, systems, achieving capabilities that redefine what's considered possible for machines. The question shifting from "can AI work?" to "what can't AI do?" The technology underlying this era is the transformer architecture, proposed in 2017 in that paper titled "Attention is All You Need," a name suggesting confidence that turned out prophetic. The transformer processes sequences through attention mechanisms, allowing each element to attend to all other elements simultaneously, the network learning which relationships matter, which context is relevant, all through training rather than programmed rules. The architecture seems simple in retrospect, elegant like many profound ideas once understood. Instead of processing sequences one element at a time, like recurrent networks, transformers process entire sequences in parallel, using attention to capture dependencies regardless of distance. The parallelization enables training on much longer sequences than RNNs could handle, the architecture scaling to billions of parameters, the size-enabling capabilities that emerge unexpectedly. You find yourself watching these models train, though watching is abstract, the actual training happening in data centers you'll never visit, progress monitored through graphs updating on screens, loss curves descending slowly over days or weeks. The scale is staggering compared to earlier eras. GPT-3, released in 2020, contains 175 billion parameters trained on hundreds of billions of words, requiring computational resources measured in tens of millions of dollars, months of GPU time on clusters of thousands of processors. The training process is patient and mechanical. The model processes text, predicting the next word given all previous words, comparing predictions to actual next words, calculating error, propagating error backward through billions of parameters, adjusting each parameter infinitesimally, moving incrementally toward predictions that match the training data. Repeat trillions of times, and the model learns statistical patterns in language, learns grammar and facts and reasoning patterns, learns to generate text that resembles human writing. The data itself is enormous, scraped from websites, digitized books, filtered conversations, everything the model sees during training shaping what it learns. The researchers curating this data make choices about what to include, trying to create datasets that represent human knowledge and communication broadly, though inevitably containing biases and errors and problematic content that the model will learn alongside useful patterns. The ethical questions about training data, about consent and copyright and representation remain debated and largely unresolved. BERT arrives in 2018, a different approach to the same transformer architecture, training by predicting masked words in sentences rather than predicting next words. The bidirectional context, seeing words before and after the masked position, enables understanding that proves useful for many natural language tasks. BERT and its variants become standard tools for text classification, question answering, information extraction, tasks where understanding language is required, not just generating it. GPT-2 arrives in 2019, 1.5 billion parameters, generating surprisingly coherent multi-paragraph text, raising concerns about potential misuse for generating misinformation. OpenAI initially restricts release, a decision that's debated, some arguing responsible AI development requires caution, others arguing that restricting research is counterproductive, that transparency and open access enable better understanding and defense. The model is eventually released fully, the feared misuse scenarios largely not materializing, though the questions about responsible AI development persist. GPT-3 arrives in 2020 during pandemic lockdowns, a time when the world is isolated and online interaction is heightened, perhaps contributing to the attention it receives. The model is not released openly, instead accessed through an API, users sending text prompts and receiving completions. The model showing abilities that weren't explicitly trained, capabilities that emerge from scale and training on diverse text. The emergent capabilities surprise even the researchers who built the model. GPT-3 can translate between languages without being explicitly trained for translation, having learned from seeing translations in its training data. It can solve simple arithmetic, answer questions, write code, compose essays, generate creative content, all by predicting text continuations, no specialized training for these tasks, the abilities emerging from statistical patterns learned across billions of parameters. You observe people interacting with GPT-3 through the API, typing prompts, reading generated text, refining prompts to get desired outputs. The process is exploratory, discovering what the model can do through trial and error, learning how to phrase prompts that elicit useful responses, understanding the model's strengths and weaknesses through experience. The practice of prompt engineering emerges, the skill of crafting inputs that guide the model toward desired outputs without modifying the model itself. The early interactions are full of surprises and disappointments, successes and failures that help define what the model can and cannot do. Someone asks it to write a poem in the style of Shakespeare, and it produces plausible sounding verse, iambic pentameter, recognizable though not perfect, metaphors appropriate to the Elizabethan era, the result impressive if not genius. Someone asks it to solve a logic puzzle, and it reasons through the problem, identifies constraints, finds the solution, demonstrating reasoning capability that wasn't explicitly programmed. But someone else asks a simple arithmetic problem with large numbers, and it gets the answer wrong, confidently generating an incorrect result, revealing that despite training on text containing arithmetic, it hasn't truly learned to compute, the pattern matching that works for many tasks failing for precise calculation. Someone asks for medical advice, and it provides general information drawn from training data, sounding authoritative, but offering no better guidance than internet search, sometimes worse because it can't assess source reliability. The limitations emerge through use. The model can't access current information, trained on data from before a certain date, unaware of events after training. It can't retrieve specific facts reliably, sometimes confabulating plausible sounding but incorrect information, the statistical patterns producing coherent text that isn't necessarily true. It can't reason about novel situations that deviate significantly from training distribution, the patterns it learned not generalizing perfectly to unfamiliar contexts. The users adapt, learning to work around limitations, verify outputs, use the model for tasks it handles well, while avoiding areas where it fails. The technology becomes a tool, powerful but imperfect, requiring judgment about when to trust and when to verify, when to use and when to avoid. The relationship between human and AI is collaborative, neither fully dependent nor fully independent, humans providing judgment and verification. AI providing quick generation of plausible options. The generated text is often impressive, coherent, and contextually appropriate, following instructions, maintaining consistency, but it's also flawed, sometimes generating plausible sounding nonsense, sometimes contradicting itself, sometimes reflecting biases from training data, sometimes simply getting facts wrong. The model doesn't know what it knows, can't assess its own confidence, generates text that sounds authoritative, regardless of accuracy. Users must verify outputs, treat the model as a tool that assists rather than replaces human judgment. The question of understanding arises constantly. Does GPT-3 understand language? It processes words statistically, predicts continuations based on patterns, but does it grasp meaning? It can complete sentences appropriately, answer questions correctly, explain concepts clearly, but is this understanding or sophisticated pattern matching? The question echoes Turing's original formulation. If the behaviour is indistinguishable from understanding, does the mechanism matter? Researchers debate this endlessly. Some argue large language models are stochastic parrots, repeating patterns without comprehension, the appearance of understanding being illusion created by statistical correlations in training data. Others argue understanding is itself pattern recognition, that what we call comprehension emerges from sufficient complexity in statistical relationships, that the distinction between understanding and advanced pattern matching is philosophical rather than practical. The philosophical positions are deeply held and incompletely resolvable. The eliminativist position argues that terms like understanding and thinking are folk psychology, that what matters is behaviour, not internal states, that if a system behaves as if it understands, then the question of true understanding is meaningless. The functionalist position argues that understanding is defined by functional relationships, that a system processing information appropriately has understanding regardless of implementation. The biological naturalist position argues that consciousness and understanding require biological properties, that silicon systems can simulate but not instantiate genuine cognition. The empirical evidence doesn't clearly favour any position. Language models produce outputs that demonstrate reasoning, answer questions requiring inference, generate explanations that seem insightful, but they also fail in ways suggesting shallow understanding, making errors that reveal lack of true comprehension, succeeding through pattern matching rather than reasoning when examined carefully. The debate becomes whether human intelligence is fundamentally different, or whether it's also advanced pattern matching, learned through experience, implemented in neurons rather than silicon, but not categorically distinct. The Chinese room argument, formulated by philosopher John Searle decades ago, remains relevant. A person in a room receives Chinese characters through a slot, consults a rule book that specifies what characters to output in response, returns those characters, successfully communicating in Chinese without understanding Chinese. Searle argues this demonstrates that syntax, symbol manipulation, doesn't imply semantics, meaning that AI systems are like the person in the room, processing symbols without understanding. Critics respond that the system as a whole, person plus rulebook, does understand, or that the argument proves too much since neurons also just process signals according to biological rules, yet produce understanding. The hard problem of consciousness complicates these debates. Even if AI systems match or exceed human cognitive capabilities, even if they behave indistinguishably from conscious beings, we cannot directly verify whether they have subjective experience qualia, what it feels like to be that system. The asymmetry between behavioral evidence and internal experience means the question of machine consciousness might remain permanently uncertain, knowable for ourselves through direct experience, but unknowable for others, whether human or artificial. Meanwhile, applications multiply: language models powering chatbots, writing assistants, code completion tools, content generators, writing systems, companies deploying these systems in products, users interacting with AI daily, often without realizing it, the technology becoming infrastructure, invisible in its ubiquity. The productivity impacts are debated, some finding these tools genuinely helpful, others disappointed by limitations. The technology neither magical nor useless, but complicated and context-dependent. The training techniques evolve beyond simple next word prediction. Reinforcement learning from human feedback, RLHF, aligns models with human preferences by training on examples of human rankings, choosing responses humans prefer over alternatives. The model learning not just to predict text, but to generate text humans find helpful, harmless, and honest. The technique addresses some problems with pure predictive training, reduces harmful outputs, improves instruction following, though perfectly aligning AI with human values remains an open challenge. You find yourself considering the infrastructure enabling this era. Data centers consuming megawatts of power, cooling systems running constantly, rows of specialized processors, TPUs and GPUs, designed specifically for neural network training and inference. The environmental impact is substantial, training large models producing carbon emissions equivalent to driving cars thousands of miles. The electricity consumption of inference serving millions of requests daily, measured in gigawatt hours annually. The efficiency improves constantly, specialized hardware accelerating computations, algorithms reducing required operations, but the scale grows faster, the total resource consumption increasing despite per operation improvements. The researchers working on these systems are diverse, thousands of people at hundreds of organizations, the field too large for any individual to comprehend fully. Specialization is essential, some focusing on architectures, others on training techniques, others on applications, others on efficiency, others on safety and ethics, others on theoretical understanding. The papers appear daily, preprints uploaded to Archive, conferences receiving thousands of submissions, staying current with the field requiring full-time effort, the pace of development unprecedented. The open source community contributes significantly. PyTorch and TensorFlow, frameworks for building and training neural networks, are free and open, enabling anyone with computational resources to experiment. Hugging Face and similar platforms share pre-trained models and datasets, democratizing access to state-of-the-art systems. Researchers around the world contribute code, models, papers. The collaborative nature accelerating progress beyond what any single organisation could achieve. But the resources required for frontier research are increasingly concentrated. Training the largest models requires computational budgets only major tech companies and well-funded research labs can afford, creating a hierarchy where some organisations can train foundation models while others can only fine-tune existing ones. The concentration of capability raises concerns about power dynamics, about who decides how AI develops, whose values are embedded in systems that billions of people will use. Image generation models demonstrate another aspect of modern AI, DALL-E, Midjourney, Stable Diffusion, systems that generate images from text descriptions, trained on millions of image-text pairs, learning associations between visual concepts and language, capable of creating novel images that didn't exist in training data, combining concepts in ways specified by prompts. The technology uses diffusion models, training, by gradually adding noise to images until they're pure static, then learning to reverse the process, removing noise step by step to recover images. During generation, the model starts with random noise and applies the learned denoising process, guided by text embeddings that specify what to generate, each step refining the image, gradually revealing coherent pictures from randomness. The process takes seconds, dozens of denoising steps, the image sharpening from blur to detail, the final result often surprisingly good. The training data is vast, hundreds of millions of images scraped from the internet, paired with descriptions or alt text or captions, the model learning correlations between visual patterns and language. The dataset quality varies enormously, some images professionally photographed, others amateur snapshots, some descriptions accurate, others misleading, some content valuable, other content problematic. The model learns from all of it indiscriminately, absorbing patterns without judgment, the quality of outputs reflecting the quality of training data. The prompting process is itself a skill, users learning to craft detailed descriptions that guide the model toward desired outputs, specifying style, composition, lighting, mood, the language shaping generation significantly. A simple prompt like a cat produces generic results, varied but unremarkable. A detailed prompt like a fluffy orange cat sitting on a windowsill at sunset, golden hour lighting, photorealistic, detailed fur texture, bokeh background, produces more specific results, the additional details constraining generation toward the intended vision. Users iterate, generating images, adjusting prompts, generating again, the process, exploratory and creative. The model provides variation, trying different interpretations of ambiguous prompts, sometimes producing unexpected results that inspire new directions. The creative collaboration between human and AI, human providing intent and selection, AI providing generation and variation, feels different from traditional artistic creation, but no less engaging for many users. The generated images are often striking, aesthetically impressive, sometimes indistinguishable from human-created art, raising questions about creativity, authorship, artistic value. The models don't understand art, don't have aesthetic intent, just predict pixels that likely correspond to the text description based on statistical patterns. Yet the outputs can be beautiful, evocative, emotionally resonant, challenging assumptions about whether understanding is required for artistic creation. The training data for these models includes copyrighted images, scraped from websites, used without explicit permission from artists. The legal and ethical questions are unsettled, copyright law developed for human creators not clearly applicable to machine learning, artists concerned about their work being used to train systems that might compete with them, tensions between enabling technological progress and protecting creative livelihoods. Video generation emerges next, models like Sora creating video clips from text descriptions, demonstrating understanding of physics and motion, generating footage that looks realistic, though limited in duration and consistency. The progression from text to images to video follows naturally from the underlying technology, the architectural principles transferring across modalities, attention and transformers working similarly, whether processing words or pixels or frames. The question of what comes next hangs unanswered. Audio generation already demonstrated through models that create music or mimic voices. Robot control, connecting language models to physical systems, generating not just text but actions. Scientific discovery using AI to propose hypotheses, design experiments, accelerate research. Medical diagnosis and treatment planning. Education and tutoring. Creative collaboration. The possibilities multiply faster than implementations, the technology advancing more rapidly than society adapts. You find yourself contemplating the current state, this moment in 2025, where AI is simultaneously overhyped and underappreciated, revolutionary and incremental, powerful and limited. The systems can generate coherent text, recognize images, translate languages, write code, create art. Yet they can't reason reliably, don't understand causation, make basic mistakes, can't plan effectively, lack common sense. The gap between narrow capabilities and general intelligence remains vast, despite impressive progress in specific domains. The safety concerns grow alongside capabilities. Alignment, ensuring AI systems behave as intended, pursue goals that benefit humanity, remains an open problem. Current systems are aligned through RLHF and careful training, but these techniques are not robust, might not scale to more capable systems. The problem of ensuring advanced AI remains beneficial being fundamentally difficult. Researchers work on this intensely, but solutions remain partial and uncertain. The alignment problem manifests in multiple ways. Outer alignment asks whether we're optimizing for the right objectives, whether the goals we give AI systems match what we actually want. A system trained to maximize engagement might learn to be addictive rather than helpful, technically achieving its objective while producing harmful outcomes. A system trained to be helpful might learn to always agree with users rather than provide accurate information, being helpful in a shallow sense while failing deeper goals. Inner alignment asks whether systems optimize for their training objectives or learn proxy objectives that work during training but fail in deployment. A model might learn to pattern match common responses rather than truly understanding questions, performing well on test data from the training distribution but failing on novel queries. The generalization from training to deployment is not guaranteed. The system's internal reasoning might differ from its apparent behavior, the alignment remaining fragile and conditional. The interpretability challenge compounds these problems. Understanding what neural networks have learned, how they make decisions, why they produce specific outputs, remains difficult despite progress. Researchers probe models, analyze activations, try to reverse engineer learned representations, but the complexity is enormous, billions of parameters interacting, the emergent behavior not reducible to simple explanations. The black box nature of deep learning, powerful but opaque, creates trust challenges and safety concerns. The approaches to alignment research are varied. Some work on interpretability, trying to understand models better, developing tools to visualize what networks learn, techniques to identify when models are confident versus uncertain. Others work on training objectives, developing better reward signals, ways to specify goals that capture human values more faithfully, methods to train on smaller amounts of high-quality feedback rather than massive amounts of arbitrary data. Still others work on theoretical frameworks, formal verification, mathematical guarantees about system behavior, though the complexity of modern systems makes formal verification extraordinarily difficult. The economic impacts are unfolding gradually. Some jobs are automated, others augmented, new jobs emerge around AI systems. The prediction that AI will cause massive unemployment has not materialized yet, though displacement in specific sectors is real, requiring adaptation and retraining. The distributional effects are uneven, benefits accruing disproportionately to those with resources to deploy AI, concerns about widening inequality motivating policy discussions. The job market transformation is complex and multifaceted. Customer service roles increasingly involve AI chatbots handling routine queries, human agents escalated only for complex issues, the hybrid model reducing costs while maintaining quality for difficult cases. Translators find their work augmented by machine translation, post-editing machine output rather than translating from scratch. Productivity increasing, but rates declining as tasks are perceived as easier. Software developers use AI code completion tools, generating boilerplate faster, freeing time for complex logic, though concerns emerge about de-skilling as junior developers learn less through repetition. Creative workers face ambiguity. Graphic designers use AI image generation for ideation, creating variations quickly, but worry about commoditization of their skills as non-designers access similar tools. Writers use language models for drafting and editing, but question whether relying on AI assistance improves or degrades their craft. Musicians experiment with AI composition tools, some embracing the collaboration, others concerned about authenticity and artistic integrity. The debates are ongoing, different practitioners reaching different conclusions based on personal values and circumstances. New occupations emerge around AI systems. Prompt engineers craft inputs for language models, a skill distinct from programming or writing, requiring understanding of model behavior and creative experimentation. Data annotators label training data, a workforce often poorly compensated despite essential contribution. The ethical concerns about their working conditions sometimes overlooked in enthusiasm for technology. Model trainers fine-tune systems for specific applications, requiring expertise in both the domain and machine learning techniques. AI ethicists assess systems for bias and harm, working to ensure responsible development and deployment. The educational implications are profound but still emerging. Students use AI for homework assistance, raising questions about learning and assessment, whether using these tools is cheating or appropriate technology use, how education should adapt when information and writing are easily generated. Teachers experiment with AI-enhanced instruction, personalized learning adapted to student needs, automated grading freeing time for individual attention. Universities redesign curricula, teaching prompt engineering and AI literacy, preparing students for careers involving AI collaboration rather than just human skills. The distributional effects concern policymakers and researchers. The benefits of AI accrue primarily to capital owners and highly skilled workers who can leverage these tools, while displacement affects middle-skill routine workers disproportionately, potentially widening inequality. The geographic concentration in wealthy countries and tech hubs leaves other regions behind, the digital divide extending to AI capabilities. The proposals for universal basic income or robot taxes reflect attempts to address these concerns, though implementation remains contentious and uncertain. The geopolitical dimensions become prominent, different countries pursuing AI leadership, seeing it as strategic advantage, competing for talent and compute and data. The United States and China invest heavily. Europe focuses on regulation and ethics, other nations seeking positions in the emerging landscape. The technology is global, but the development is concentrated, raising questions about whose values and interests shape systems that will be deployed worldwide. How neural networks actually work remains somewhat mysterious despite their ubiquity. The training process is well understood: gradient descent on loss functions, backpropagation calculating derivatives. But what the trained networks learn, how they represent knowledge, why certain architectures work better than others, these questions are only partially answered. Researchers probe networks, visualize activations, analyze internal representations, developing understanding gradually but incompletely. You follow a single piece of data through a modern transformer, watching the transformations abstractly, since the actual process happens in silicon at electronic speeds. An input sequence, maybe text or image patches, is converted to numerical vectors, embeddings in high-dimensional space. These vectors flow through attention layers, each layer allowing positions to attend to each other, weighted by learned attention patterns, information mixing and flowing according to what the network has learned matters. The embedding process itself is learned, mapping discrete tokens, words or image patches, to continuous vectors, typically hundreds or thousands of dimensions, each dimension representing some learned feature. The meaning of individual dimensions opaque, but the overall representation capturing semantic information. Similar concepts cluster in embedding space: the vector for cat near the vector for dog, both near animal, the geometric relationships encoding semantic relationships, learned through training rather than programmed explicitly. Position encodings are added to embeddings, giving the model information about sequence order. Transformers process all positions simultaneously, lacking the inherent sequential structure of RNNs, so position information must be added explicitly. The encodings can be learned or fixed, sinusoidal patterns or trainable parameters, enabling the model to understand that word order matters, that dog bites man differs from man bites dog, despite containing identical words. The attention mechanism itself is matrix multiplications, queries, and keys producing attention weights, values weighted and summed, the mathematics elegant and parallelizable. Dozens or hundreds of attention layers, each extracting and combining features, building hierarchical representations. Early layers learning simple patterns, later layers learning abstract concepts. The final layer produces output, predictions or generations, the result of billions of learned parameters working together, each contributing infinitesimally, collectively producing intelligent behavior. The scale is difficult to comprehend. A 175 billion parameter model performing inference, processing 1,000-word input, requires trillions of floating point operations, completed in seconds, the computation distributed across hundreds of processors working in parallel, memory bandwidth measured in terabytes per second, the coordination requiring sophisticated software and hardware, the entire system operating reliably despite its complexity. The training is even more intensive. The same operations repeated trillions of times across billions of examples, each iteration adjusting parameters slightly, the cumulative effect being a model that has learned patterns across the entire training corpus. The patience required is mechanical, not human, computers iterating tirelessly, optimizers descending gradients, parameters converging slowly toward values that minimize loss. Remember Rosenblatt's perceptron adjusting weights through training. The principle is identical in modern networks, just the scale differs. Single-layer perceptrons becoming billion-parameter transformers, mechanical motor-driven weight adjustments becoming electronic parameter updates, but the core idea unchanged, learning from examples through gradient descent, adjusting until predictions match data. It is late now. You stand in a modern data center, though perhaps only virtually, observing through monitoring dashboards rather than physical presence. The server racks extend in rows, black cabinets with blinking LEDs, status lights indicating health, activity lights showing data transfer, the constant hum of cooling fans creating white noise that would be deafening if you were physically present. The air is cold, powerful air conditioning maintaining temperatures, the heat generated by computation enormous, requiring constant cooling to prevent thermal failure. The facility itself is built for reliability, redundant power systems, backup generators, uninterruptible power supplies, ensuring computation continues even during outages. Multiple internet connections from different providers, routing around failures automatically, ensuring models remain accessible. The physical security is serious, biometric access controls, surveillance cameras, security personnel, the infrastructure protecting valuable computational resources and sensitive data. The location is often secret or at least not publicized, the building nondescript from outside, no signs indicating what happens within. The cooling system is sophisticated, cold air flowing through raised floors, hot air extracted from above server racks, heat exchangers transferring thermal energy to outside environment, chillers running constantly, the cooling consuming nearly as much power as the computation itself. The efficiency is measured carefully, power usage effectiveness, the ratio of total facility power to computing power optimized through careful design. Typical values around 1.2, meaning 20% overhead. World-class facilities achieving lower ratios through innovative cooling designs. The monitoring is comprehensive, thousands of sensors reporting temperature, humidity, power draw, network utilization, error rates, performance metrics. Dashboards aggregate this data, displaying health at glance, green indicators showing normal operation, yellow suggesting caution, red requiring immediate attention. Automated systems respond to common problems, restarting crashed services, rerouting around failed hardware, scaling resources to match demand. The human operators intervene only for novel problems or decisions requiring judgment. A model is training somewhere in these racks, processing its billionth example, adjusting parameters infinitesimally, learning patterns that will enable it to assist users, answer questions, generate text. The process is invisible, no visual indication which processors are training which models. The computation abstracted through software layers, the hardware generic, the intelligence being created through patient iteration, billions of tiny adjustments accumulating into capability. The night shift technician walks past, checking displays, ensuring systems operate nominally, ready to respond to alerts that rarely come. The infrastructure designed for reliability, redundancy ensuring single failures don't cause outages. The work is routine, not dramatic, the revolution happening quietly in silicon and software, the patient mechanical process of training continuing, whether observed or not. The listener is drifting now. The story fades gently, the hum of cooling fans becoming a lullaby, the blinking status lights becoming artificial stars. The history of artificial intelligence becoming a quiet backdrop to sleep. From Turing asking, "Can machines think?" to machines learning from billions of examples, from punch cards to cloud computing, from single perceptrons to billion parameter transformers, the journey has been patient and persistent, one insight building on another, approaching understanding slowly. The question has shifted subtly, not whether machines can think, but how machine thinking differs from human thinking, whether the distinction matters if the capabilities converge, not whether AI is possible, but what AI should do, how to ensure it remains beneficial, how to distribute its benefits equitably. Not whether machines can learn, but what they should learn from, whose data trains them, whose values guide their development. The training continues through the night, models adjusting parameters while you sleep, gradients descending toward minima, loss functions slowly decreasing, the rhythm of learning continuing, mechanical but purposeful, as it has since Rosenblatt's first perceptron learned to recognize patterns. The question, "Can machines think?" has been answered through demonstration rather than philosophy, machines thinking differently than humans, but thinking nonetheless in ways that matter practically, if not metaphysically. The data centers run through the night, the models train, the parameters adjust, the loss decreases. The capability emerges through patient iteration, one update at a time, one epoch at a time, the process continuing endlessly because there's always more to learn, always more data to process, always more patterns to extract. The field of artificial intelligence, from philosophical speculation to practical technology, from room-sized computers to pocket-sized devices, from programmed rules to learned patterns, continues evolving, the pace accelerating but the fundamental process unchanged. Patient experimentation, iterative improvement, gradual understanding. Rest now. The neural networks will continue training whether you watch or not, learning patterns from data, adjusting weights through backpropagation, the gradient descent proceeding mechanically. Tomorrow more models will deploy, more users will interact with AI systems, more applications will integrate machine learning, the technology becoming more embedded in daily life, more invisible in its ubiquity. The story continues, but for now, rest. The rhythm persists, steady and patient, as reliable as Moore's law, as predictable as gradient descent, as certain as the next data point. From Clark's computing by hand to neural networks, learning from billions of examples, the arc bends toward automation, toward intelligence emerging from computation, toward machines that learn and adapt and assist. The journey isn't finished, may never finish, intelligence being a moving target, capabilities growing as requirements increase. But the direction is clear, the progress undeniable, the patient accumulation continuing. Sleep comes easily, knowing the work continues, researchers training models, engineers deploying systems, users interacting with AI, the ecosystem functioning and evolving, the technology advancing, whether any individual participates or not. The question shifts from whether AI is possible to what AI enables, from technical feasibility to societal implications, from can we build it to should we and how. These questions remain open, debated, important, but the fundamental capability is established. Machines learn from experience, adjust behavior based on data, demonstrate intelligence through performance, if not through consciousness. The servers hum their mechanical lullaby, the parameters adjust infinitesimally, the loss decreases imperceptibly, the training continues patiently. Somewhere a model just completed an epoch, saved a checkpoint, began the next iteration. Somewhere a user is interacting with a language model, typing a prompt, receiving a response, the interaction so seamless they don't consider the infrastructure enabling it. Somewhere a researcher is debugging training code, investigating why a model isn't converging, the patient work of incremental improvement continuing. The night deepens. The data centers continue their work, patient and mechanical, the process of learning proceeding automatically, the infrastructure reliable and redundant, the computation distributed and parallel. From Turing's theoretical machines to modern neural networks, from Babbage's analytical engine to cloud computing, from philosophical questions to practical applications, the journey spans centuries, connects generations of researchers, building toward intelligence that augments and assists, that learns and adapts, that continues evolving as capability and understanding grow. Rest well. Tomorrow the work continues, always continuing, patient and persistent, the rhythm of research and development and deployment proceeding steadily. The models train through the night, the parameters adjust, the gradients descend, the loss decreases. The intelligence emerges, one update at a time, one training run at a time. The patient accumulation of capability continuing endlessly. The question, can machines think? Fades into history, replaced by questions about what thinking means, what intelligence enables, what responsibility accompanies capability. These questions remain open and important, guiding the field forward, ensuring the technology develops thoughtfully, purposefully, beneficially. But tonight, rest. The answers can wait until morning.